Hello, everybody. This is Corbin Whittington with Science Time. I'm sorry it's been a little while since I've uploaded, just been lazy, I guess. But today we're going to get into a really interesting topic of the thermodynamics of black holes. Now, if you don't know what thermodynamics is, no worries. We'll get over that. And if you don't know what black holes are, then I suggest you watch my previous videos to get a good grip or understanding. So, first things first, we need to get into thermodynamics, which is basically, if I were to sum it up in a sentence, it's how heat works. So you don't need to know the laws for this episode. It would be useful, but you don't really need to. But how heat works is things go from hot to cold. That's the flow of temperature. So let's say, for example, you have a piece of ice and you drop it into some water. Well, what would happen is the ice would gain heat from the surrounding water inside of it, and thus it would melt inside of the water, and then there would become an equilibrium of temperature, and everything is trying to get to an equilibrium. That's why whenever you have a heater on your house, the heat disperses throughout the house, and your house becomes warm, rather than just one spot becoming really, really hot and just keeping all the energy inside of it. And that's pretty much just why heat disperses. So let's get into the first question I have today, which is, what are the thermodynamics of a black hole? Now, the thermodynamics of a black hole involve Hawking radiation, which I've gone over in my previous video. It's basically how a black hole dies. So black holes don't live infinitely. They have to lose energy over time. And this goes with a long series of complicated equations, but basically all you guys need to know is that Hawking radiation allows the energy of a system from a black hole, and it allows it to escape. And it allows it to escape through photons. And this is where the radiation takes place at. So what happens, how much heat is given off a black hole whenever it is dying, or aka, what are the thermodynamic properties of a black hole? Well, to answer this question, we need to look at whenever a black hole isn't dying. So if we take a look at, let's say, a supernova-sized black hole, we can see that they have temperatures of lower than 1.4 times 10 to the negative 14th power Kelvin. And Kelvin's really, really cold, so 0 degrees Kelvin is absolute zero, where there's no energy in a system, and that means that it's the coldest something can possibly get. So let's say, for example, you have 0 degrees Celsius and 0 degrees Kelvin. 0 degrees Celsius is a lot hotter than 0 degrees Kelvin, and I guess that's just a good reference point. So whenever you have this such low value of Kelvin, it's really, really cold, which doesn't make sense because black holes are huge, right? That means that they have a lot of mass, and that means that they should have a lot of energy inside of them, which they do. But the thing with temperature inside black holes is that it's inversely proportional to the mass of it. And what this means is the more massive a black hole is, the colder it gets. And this actually makes some sense because if it's absorbing all the energy inside of it or around it, then that means that it should be absorbing its everything, right? So whenever we take a look at this, it means that it's really, really cold. But let's take a look at something that has a relatively higher temperature. Let's take a look at a black hole with the mass of an asteroid. For example, I'll use the asteroid Ceres, which has a mass of 1,958 times 10 to the 20th kilograms, which is pretty large. A black hole with this mass, would have a temperature of 122 degrees Kelvin, which is really, really low. It's still freezing, but it's a lot higher than the temperature of previously recorded ones. Well, if you were to get a black hole that small, which theoretically wouldn't happen because it would have to be super dense. But it's still a lot hotter than a supermassive black hole. So we're going to get into the second question of today, which is what would happen if a black hole absorbed a sun. Because suns are really, really hot, and a black hole is really, really cold, as we found out. So what would happen to the equilibrium of temperature there? Well, if you're thinking about it correctly, then there would be an equilibrium of temperature and both things would stabilize out. However, this thinking would not be correct. What happens whenever a black hole absorbs the sun is the black hole tears apart the sun because the gravity is so immense that it allows it to basically tear it apart. And this means that there are a lot of hot objects, but it's not nearly as hot as it would be. And this allows the black hole to, absorb it. There is no equilibrium of temperature because the black hole gets more massive. And if we remember from previously, the mass of a black hole is inversely proportional to its mass. So whenever it absorbs the sun, it actually gets a lot colder, which is strange to think about. And the last question we have for today is, what would the thermodynamic properties be of one black hole that had another black hole absorbed inside of it? Well, for this we need to think about black holes as objects, really, really massive objects, because that's basically what they are. So whenever you have a really massive object that's absorbed inside of a black hole, we know that it gets colder. But we also know that they emit Hawking radiation, which emits a little bit of heat. So what would happen is whenever these two black holes collide, they would form a supermassive black hole, which would become so cold that it reaches almost absolute zero, which is what the supermassive black hole I was talking about earlier does. But what would happen is, over time, it would start to decay because nothing can stay forever in this universe, not even black holes. And over time, this decaying factor would get larger and larger the smaller it was. So that means that it would release a lot more energy. So I guess whenever you're thinking about this, a supermassive black hole is very, very cold. The longer time that it has to decay, the hotter it gets. So that's how a black hole, like with the massive asteroid Ceres, for example, can reach temperatures of 122 degrees Kelvin. And that's why whenever black holes eventually decay, they can become very, very hot. That's it for this video. I hope you guys enjoyed today's lesson. If you learned anything, please leave it down in the comments. If you liked it, leave a like maybe. And have a good day, y'all.